So folks, continuing on with our review, a function that we write in this form is called a power series, and we would say that it's centered at x equals a. Because of this expression x minus a here, a is the value that it's centered at. What you can notice about a power series is there's several components. There's this c sub k, and then there's the x minus the value that it's centered at raised to the kth power. So notice that this term right here is simply a power function in terms of the variable x. And as k takes on different numbers, this would give me a different power term for each value of k. We call each one of these ck values, or the cith values, the coefficients of the power series. Usually when we're constructing a power series representation of a function, coming up with the coefficients is the most important part. And that'll be the case while we deal with these in differential equations. So let me just add that you can think of a power series as then an infinitely long polynomial. And just to give you something a little bit more concrete than this abstraction, if we looked at this function right here, the sum from k equals 1 to infinity of x to the k, this is a power series centered at 0. And each coefficient, each ci value, is just 0. I'm sorry, each ci value is just 1. So if you wanted to expand this out, you would write it as 1 times x to the 0th power is 1, plus 1 times x to the first power, plus 1 times x to the second power, plus 1 times x to the third power, plus dot, dot, dot. And here you can see where I give you the statement that we can think of it as an infinite polynomial. Now, this power series that I came up with on the spur of the moment is not a good power series, because this infinite polynomial never converges for any value of x other than x equals 0, the value that it's centered at. So in general, if we want to think of our power series as a function, the most important question we ask about any function is what's its domain. And as far as a power series is concerned, its domain is precisely the values of x that we could plug in to this series so that the series converges to a finite value. And so typically when we're dealing with a power series, we're always asking the question, what values of x am I allowed to plug into it so that I get convergence? For that to happen, we need this limit of this infinite sum to converge for any choice of x value. And hastily going through a few of the topics, and my mouse is stuck again. Hastily going through a couple of the topics, we have only a few different things that could happen for a power series. First of all, notice that if I were to take this power series as I wrote it up above here, g of x, and I plug in the value for a, then I'd have a minus a is 0. So every power series will converge, meaning that the function g of x is defined at the value that it's centered at, because all you're doing there is adding up infinitely many zeros. If it converges for more x on some interval, then we might be able to say, for instance, and this will be one of the three, so let me say this. How do I have it here? One of these three will occur. Where I might be able to find an r value that we'll call the radius of convergence, and for any choice of x within this interval right here, we have, if I take any x value and plug it into the power series, we would get convergence. And if I took any x value that's outside of the closure of that interval, I would not get convergence. The next option is that it might converge for all real numbers, meaning regardless of what value I choose for x right here, I'm guaranteed that the series converges. As far as somebody coming up with a power series to represent something, when your radius of convergence is infinity, that's the best possible scenario. You don't have to be careful about where you evaluate that function at. And if it's not a fixed radius r, or the radius isn't infinity, then the radius of convergence is 0. So it will always be one of these three. These types of power series are absolutely useless. They don't in any way convey any information for us to use. And I guess I forgot to, G is where I make this statement here. It will only be a radius of convergence or at some radius of convergence. This should not be, this should just be an x contained in. Sorry about that, folks. Or the radius of convergence will be all real numbers. So now, folks, I want to give an example of finding both the radius of convergence, which we discussed above loosely, and the interval of convergence, which we'll define in sort of in passing, for this particular power series right here. First thing I want to do is just, one, convince you it's a power series. So let's put it in the form. We can rewrite it as the sum from n equals 4 to infinity, and we would have 1 over the square root of n times x minus 3 to the n. So notice this power series did not start at 0. It's customary to start them at 0, but in this case we did not. And these would be your c sub I values. These are the coefficients of the power series, 1 over the square root of n, so depending on the value of n, the coefficient changes. And then here we have the power factor of each term of the power series. And so because of this way this is set up, we have that the power series is centered at x equals 3. So in this problem, I'm asked to find the radius of convergence and then the interval of convergence. Typically, to find the radius of convergence, you will go ahead and do the ratio test. And to save us a little bit of time, I've already worked that. So to do the ratio test, we'll look at the limit of the ratio of the next term over the current term in absolute value. So here I've set that up. Here is my a sub n plus 1, where I replaced all the n's in the expression with n plus 1. And here's my a sub n. Similar to what we saw last time, I took and inverted and multiplied that denominator. And just as before, we'll have some terms canceling. Most importantly, notice we've got this x minus 3 to the n plus 1 all over x minus 3 to the n. That just gives us x minus 3 as a factor here. Notice this is all inside of that absolute value. And then I wrote the ratio of the two square root terms that involve n. The next move is one that's different as well from what we've seen before, in that this expression x minus 3 does not have an n in it, which is our limiting value. And so as far as n is concerned, this is a constant, and so I can factor it out of the limit. Notice, though, that it comes out with this absolute value here. So I'm left with the limit of this ratio multiplied by that expression. So there's that x minus 3 expression, and that limit. What I did here was just go ahead and rewrite these under a single square root sign. And then the next step is one that we borrow from Calc 1, which says the square root function is continuous on its domain, and as these expressions get larger, we remain in the domain of this square root function, and limits pass through continuous functions. And so I went ahead and passed this limit through the square root function. Now I'm ready to take this limit the way we do in Calc 1. We multiply by 1 over n, which is the highest exponent seen in the denominator. And that gives us, after I've cleaned that up, this expression here. It's a little hard to read. That's our x minus 3. Oh, by the way, at the point where I wrote this as a single square root, I dropped the absolute values because it's implicit that whatever comes out of a square root function is either 0 or positive. So I've dropped the absolute values on that. If I didn't have this square root, I would need to retain those absolute values. So after I do the Calc 1 trick of multiplying by 1 over n to the highest exponent in the denominator, this is what I'm left with. The limit evaluates this way through direct substitution, and so we get just the, and I'm missing some absolute values on there, fix that, the absolute value of just x minus 3. So hopefully you'll pause the video and copy that down. But the hard part is, or the more interesting part is what comes next. And remember that we are doing the ratio test, and the ratio test gives the conditions for which we have convergence of our original series up to a certain point. That test tells us if the limit, which in our case came out to be this expression here, if that limit is less than 1, then we're guaranteed convergence. And if this limit is greater than 1 or is divergent, then we're guaranteed divergence. And if this limit is 1, then the ratio test, which is what we just performed, is inconclusive. So we need this expression to be less than 1 to guarantee convergence. And in fact, this is, at this point, we can go ahead and identify this is our radius of convergence. The radius of convergence here is 1. And I'd like to show you what I mean then when I talk about the interval. So if we were to go ahead and set this up as an absolute value inequality, this is what we get. Oops, I've dropped it. Once we put it as, so remember that the absolute value inequality is shorthand for this. If I add 3 to both sides, I get 2 is less than x, which is less than 4. And so this, here you can see what we mean by the radius of convergence, because I'm guaranteed convergence for any x value within this interval right here. I'm guaranteed by the ratio test. Now, the interval of convergence says we also need to check whether we have convergence at these two endpoints. And so what I need to do is I need to examine them separately. So again, if we go look at this statement up here, we found that we had a radius convergence R, and so we know that we at least have convergence on this interval, and we have divergence outside the closure of this interval, but we still don't yet know whether if we do A plus R or A minus R, whether or not the series will still converge. So usually what you have to do then, and hopefully you saw this in Calc 2, is you have to check your endpoints separately. Let's go ahead and let x equal 2. And if we re-examine our original root function, we would have negative 1 to the n all over the square root of n, where I let x be 2, and so that made this expression inside the nth power, negative 1, all over the square root of n. So that's the sequence. Let's write that as a series. It's more appropriate too. So let's write that as the sum from k equals, I think we started at n equals 4 to infinity. But this series, just like we saw in one of our last examples, this series converges by the alternating series test. Why? Because 1, it alternates. 2, the non-alternating term is always positive, decreasing, and converges to 0. So we know that we're going to include 2 in our interval of convergence. But we also need to check the other endpoint, which is 4. And if we set this up, we'll have the sum from n sorry, I said n equal 4. Folks, we need to check x equal to 4. So we get n equal to 4 to infinity for the series of, and then if I add 4 to the expression in here, I just have 1 to the n, which is 1 to the n all over the square root of n, which is the same thing as the sum from n equals 4 to infinity of 1 over the square root of n, or raising 1 to any finite power is still 1. This series diverges by what was called the p-series test, which I haven't elaborated on, but if you go take a look at our p-series test, here's our p-series test, which says that a series that has this construction will converge if p is greater than 1, we have convergence, and if p is less than or equal to 1, we have divergence. In our case, our p-value, if you want to write it so that the p-value is more explicit, we have 1 over n to the 1/2. Because this p-value is less than or equal to 1, we have divergence. And so for that reason, we don't include x equal 4 in our interval of convergence. So if we go to state our interval of convergence, the interval of convergence is from 2 to 4, and our radius of convergence is 1. So let me box in green those two answers. There's our radius of convergence. There's our interval of convergence. So just to reiterate, if I built this function right here, if I built the function f of x is equal to the sum from n equals 4 to infinity of x minus 3 all over the square root of n, it was x minus 3 to the n, the domain of this function is from minus, what do we say, from 2 to 4. That's the domain of this function. If I take any x value and plug it in, I will get a finite value outputted from this function. Folks, that was probably one of the more difficult things we've done in this review video. Please, if you have any questions, let me know, and I'd be happy to go through it in more detail.